Yes, hello everyone. Welcome to this session about rainfall, stream, flow, and flood forecasting over the Nile Basin. I will start again with some few housekeeping, and then we will start our session. Please type your name, affiliation, and for our speakers and panelists, please kindly mute your mic and turn off your camera, except when you're speaking. You can use the chat room to share and exchange ideas also. You can post your question in the Q&A feature. This will be responded to by the resource person. On the behalf of the Executive Director of the Nile Basin Initiative Secretariat, I would like please to open this session. The Nile Basin Initiative, in collaboration with the government of Ethiopia, is organizing a series of webinars in the 6th Nile Basin Development Forum under the theme Rethinking Regional Investment in the Nile Basin. The Science Policy Practice Dialogue is organized to bring together NBI with its stakeholder from the Nile Basin countries and around the world also. The goal of this Nile Basin Development Forum is to enhance transformation processes in projects that will contribute to the Nile Basin Initiative shared vision, which is to achieve sustainable socioeconomic development through the equitable utilization of and benefit from the common Nile Basin water resources. The theme in this 6th Nile Basin Development Forum, water resources management, environment and wetlands, water energy food nexus, adaptation to climate change, transboundary water governance. The Nile Basin is one of the most critical transboundary water basin in Africa, with the River Nile playing a crucial role and resource for most of the economic and social activities for the countries in the Eastern and Northeastern Africa. The climate is changing, putting a range of natural and human systems at risk, and promoting communities, governments, and organizations to step up their effort to adapt. And for us here at the Nile Basin Initiative Secretariat, we are developing, or we developed the Nile Basin Riverflow forecasting system for the entire Nile Basin. At Intro, we are doing many activities also related to the flood forecasting. That said, it is equally facing adverse effect of climate change, which is expected to worsen in future should little or no efforts be done to avert the current trends. So welcome to this webinar. Let us have fruitful presentations and discussions, and let us work together to incorporate these findings in our decision-making River Basin agenda. Thank you very much. Now, please kindly allow me now to start my key note presentation. One second. Okay. Okay, thank you very much. I would like to share with you the work that we did in the Nile Basin Riverflow forecasting system. So this is the outline, introduction, some information about this Nile Basin Riverflow forecasting system, the drought monitoring and forecasting. I will just highlight here because we have a special session for that tomorrow. And I will talk about some toolkits also we developed in a collaboration with Intro. Under Goal 5 of the NBI 10 years strategy, the Nile Secretariat intends to develop a short-term to seasonal river flow forecasting. We want to provide information about the volume of stream flow. We were looking also at the lead time, which could range from few days to seasons. We also want to help managing the releases from the water storage facilities. And we want to improve also planning decisions on cropping, improving safety of water infrastructure, provides opportunities to extract water during different flow peaks. We had two phases, a preparatory phase, and then we have like a development phase. Just briefly, during the preparatory phase, we reviewed like lessons learned from international experience related to river flow forecasting, also lesson learned from current use of flood forecasting system in the Nile Basin. We looked also at the needs assessment from our stakeholders, and then we made our conceptual design. We conducted like several needs assessment workshop with our stakeholders along the Nile Basin. And in the development phase, we focused on different component. First, the inception, and then after that, the software framework and the model adapters, and then the forecast dissemination platform, and also after that, the Nile Basin operational forecast model. And then after that, we tested and implemented our system. In this also river flow forecasting system, we had a component also about the drought, and we had toolkits for dam operation and irrigation. We developed it also under this project. This is our system. It is fully automated, this system. We collected information from different resources and data. Here at the back end, we process it by using our Nile DSS model. And then with some use of API and user interface, we are disseminating our information in some web page. We are also disseminating our information through the IKP. This is the integrated knowledge portal for the NBI. On the same time, we are sending some specific information through emails to some specific selected users also. This is our Nile Basin hydrological model, which we used in this project. This is like a kind of result that we can get from this Nile Basin river flow forecasting system related to reservoir water level, related to the amount of flow at different locations, and also related to the rainfall, even like the agricultural project. This is under this project also with the collaboration of Intro. We did this drought monitoring and forecasting. And we are generating also a bi-weekly bulletin shared with our stakeholders over the Nile Basin. And also everyone can access this web page and generate also different kind of information averaging over different small subcatchment over the Nile Basin. This is like some examples of time series and comparison you can do yourself in this web page. This is the first page of the bulletin that generated automatically around every 2 weeks. This is our IKP. We also disseminate our information through this IKP. This is the integrated knowledge portal. Here, these are the toolkits. If you want to change even like the demand of water yourself, you can also receive the forecast after changing some little information here also. This is like the web page which integrate everything. On the left here, this is our Riverflow forecasting system. Here, this is our drought monitoring and forecasting. Here, this is for the toolkit kits. Here, these are some important links you can use and you can test and maybe give us feedback if you have any feedback. Thank you very much. Thank you. Now we can start our presentations. Thank you very much. We have very interesting and very nice presentation. We will start with Dr. Hubert. Please, Dr. Hubert, introduce yourself first. And the floor is yours, Dr. Hubert. Thank you.
Thank you very much, Dr. Mutadir. So my name is Hubert Lohr. I'm Executive Director from Südl Consult, located in Germany, company dealing with water resources management, mainly modeling, forecasting, and integrated water resources management. I'm in this field of work since more than 30 years now, and I have prepared a presentation which I would like to start by sharing screen now. And I hope that you can see now my presentation in the presentation mode. And I would like to say that it's a pleasure for me to hold this presentation here in this webinar. And I'm going to present an approach that was developed actually beginning in 2016. The German abbreviation for this is TASK approach. At the end of the presentation, you will find a link where you can get more information about this approach. It was completed in 2018, more or less, and is since then in operational use in parts of Germany for mining companies and basically for reservoir operators. This year, we have launched a second phase of TASK, a successor research project, in order to advance the approach into contingency planning and in order to incorporate the agricultural sector. So the presentation here is on seasonal forecast, where seasonal forecast is in this context defined, which is longer than 1 month and maximum of 9 months. And we use for the forecast hydrometeorological indices, and that is possible to extend the approach by using additionally hydrological models. So let me switch to the next page. Considering seasonal forecasts, we opted for 2 sources that you can see on the slide. The first is the NOAA climate forecast system, which comes with monthly means, provides a maximum of 9 months ahead forecast. They provide 4 forecasts a day, and it's operational and thus accessible since April 2011. The second source is the ECMWF, the long-range forecast model system there. It's from the EU. They also provide monthly means. The maximum length they look ahead is 7 months, and they provide an ensemble forecast which comes once a day. And it's also operational since 2011, here since November 2011. So some words about hydrometeorological indices first. Indices are numerical representations of hydrometeorological states, and the calculation procedure is pretty clear and well documented. So there is no, let's say, no issue and no doubt about how it works to calculate all the kinds of different indices. The World Meteorological Organization recommends, for example, the SPI, the Standardized Precipitation Index, which is actually the index that is used almost everywhere in the world to inform about anomalies of precipitation. It is important to know, and that is one crucial element, that indices use a reference period and compare a current situation against that reference period. In other words, the selection of the reference period is crucial. And for example, if a dry period is selected as reference, for example, you compare a current situation against a more or less below average dry period. And the average amount of rainfall then, in terms you get average amount of rainfall, will appear as wet. And of course, the other way around, selecting a wet period as reference results in indices that indicate below average conditions, even if rainfall is on average. So, in conclusion, the reference period should be selected very carefully. And that means what is considered normal is a crucial question. In climate change studies, usually the term normal is identified as the period between 1960 to 1990. That is considered the period which is not yet affected by any climate change conditions. But some studies simply use other periods, for example 1917 up to 2000 or 1980 up to 2010, and it depends largely on what is available, to be honest. So what is the approach of this seasonal forecast methodology? So if you look first without forecast, we look into the story without forecast first, and you see the green here, that's the observation. And from here, the observation stops. Of course, it stops at the now, at the date today, ideally. So that is past observation, that is future, what we do not know already. So when we look into the index calculation is done with a set of different aggregation periods. And what is possible, because of the inertia of usually all the hydrological systems, we get some forecast, even if we do not look into the future, because an SPI, for example, or other indices, they indicate what will later be observable in runoff due to the inertia of the hydrological system. So that is the fact when we do not consider forecast. Now with forecast, for example, the situation changes, because now, due to the seasonal forecasts from the two models here, we can extend our view, and that means we have observable information here, but also we have forecasted rain, in this case, now that goes into the future. And that means now that we can shift the aggregation period somehow more into the future, and it is up to us, and it's up to testing how good and reliable results will be when we shift more and more into the future. And that means we can push the effect and the outcome more into the future. So let's summarize what we have seen here in terms of the with and without forecast situation. First, it is possible to expand the index calculation into the future. Second, it is possible, and that's the point here, it's possible to combine reliable with uncertain information. Reliable means we combine observations with forecasts. And third, we can test how much lead time is possible, how big can the share of unreliable or future forecasts be compared to the share of known reliable information. And that means we look into different combinations of observed and forecasted values. Let me show one thing. That's an index forecast from an area in Germany. It's 3,000 square kilometer area, more or less in the mid of Germany. And what you see here, the thick red line, is the true index based only on observations. So we look into a hindcast experiment. And what you see as well is the blue line, and that indicates the calculated index with mixed values. Mixed means the first month is just 11 months of reliable information plus 1 month of forecast. And when you look 9 months ahead here, that's here, you see the 9 months forecast, which of course has 3 months of reliable observations and 9 months of forecast. And as you can see, the forecast index is adaptive. Each month, when new observations arrive, the index adjusts and provides a better representation. So once it diverts, you will see that in the next situation, it will probably adapt itself automatically. Now it will happen soon that it goes back. Yeah, as you see it now. And then it is an auto-adaptive process. And what comes next in the process chain is then to transform the index information into streamflow information. That means we go into another state, and for example, the state useful here is streamflow. The graph shows the relationship between, in this case, the SPI and the streamflow index for this catchment area of 3,000 square kilometers in Germany, where we run this approach in the operational mode. And with that relationship between the index and the streamflow index, it is possible in the next step to create a relationship between the streamflow index and finally the streamflow itself. And this is of course extremely useful when we can transform the index information into streamflow information. That is useful for water resources management or reservoir operation. And that is exactly the applications here in Germany. So the summary from my side is, first, when we look into the process chain, we select the source for in the seasonal forecast and we run bias correction. That is the crucial point that comes first. Then we assess the best lead time, which is nothing else than the combination of known records with forecasts. Then we transform the meteorological index, in this case, into a streamflow index by means of a relationship. And from here, with a second relationship, we transform it to streamflow. And with streamflow, it is eventually possible to apply a hydrological reservoir operation model. In our experience, after running this approach now since almost 3 years now, is we can state that it's good for early drought detection, but it's not applicable for single flood events. The resolution is not good enough. So we talk about flow volumes, and that is, we get good forecasts in terms of flow volumes, but we would not recommend to use high resolution hydrographs coming out of this approach. So it's all about water amount, flow volumes. And that is possible that it can be used in reservoir operation applications or in water management applications. And to close my presentation is that we saw that a lead time of 3 months results in quite good results, and in some areas even we could use it into a 6 months lead time. And it depends. It is difficult to predict that an area turns out to be 9 or 7 months forecast. We haven't seen that yet, and it's also up to, let's say, the testing, whether we get good results that come up with a 6 months lead time. So, thank you very much for your attention. If you want to know more about this approach, please pay a visit to this website, and thank you very much for your attention. And I hand over back to Mutadir. Thank you.
Thank you very much, Dr. Hubert, for this very interesting presentation. about the seasonal forecast with intelligence use of hydrometeorological indices. And thank you for sharing this very interesting and useful approach. Thank you very much. I just would like to remind our participant with some housekeeping. Please kindly type your name, affiliation, and country of residence in the chat room so that other participants can know who's present. And please use the chat room also to share and exchange your ideas. Also, you can post questions in Q&A feature, and this will be responded to by the resource persons. Thank you very much. Now we will go to our second presentation. It is by our expert from Intro, Azab Mersha. She is our water resources expert from Intro, and she will give us a presentation about flood forecasting in the Eastern Nile, and she will share with us the long experience of Intro in this field. Please, Ms. Azab, introduce yourself first, and the floor is yours. Thank you.
Thank you, moderator. Okay, let me share my screen. Can you see my screen?
Yes, very clear. Thank you.
Okay, so moderator have given a keynote speech on the river flow forecast, but I will be focusing on the flood forecast activity which we have done in Intro and covering the Eastern Nile region. So giving you a little bit history about the historical events of flooding in the region. There are lots of past severe flood occurring and causing loss of life and infrastructure in the basin. This can be caused by different reasons. One of it is movement of population to flood-prone areas that caused by overpopulated in the region. Historical events shows that we can go back to 18,000, and we can see that the flood events in the much recent years are becoming more frequent and more severe. And if you see the last flood season, which have caused a loss of life, around 100 people have died, and more than 800 people have been critically affected by flooding in the last flood season by itself. And when we talk about floods in the Eastern Nile Basin, it can be riverian or flash flood, especially in South Sudan and Sudan area. Lots of flash flood events have been happening in much recent years. So coming to activities of Intro, it all started in 2001 when Eastern Nile Council of Ministers requested for funding to advance flood management in the region. And due to the critical and the seriousness of the issue, the ENCOM decided to fast-track the flood preparedness and early warning project. And in 2016, it was decided, due to the huge project, to have it in two phases, and phase 1 and phase 2 of flood preparedness and early warning project. Now, phase 1 project have been granted a funding, and it have run from 2000 to 2010. And for phase 1 is mainly focused on non-structural measures, while phase 2 was proposed to cover structural measures to have more flood control in the region. But the project document was concluded in 2007, but funding was not secured up to now. To give you some of the achievement of phase 1, it was done in 4 major areas, having and establishing a regional flood coordination unit at Intro, which was closely linked to National Forecast Center. And it was established a forecast center in Sudan, South Sudan, and not South Sudan. In Sudan, Ethiopia, and Egypt, South Sudan was not separated at that time. And real-time forecast system was developed for at least 2 flood-prone areas in Lake Tana in Ethiopia part, Blue Nile, and in Sudan part. At that time, Nile Forecast Center was there in Egypt, and it was strengthened their capacity under this project. And we also developed emergency response and preparedness plan for selected flood-prone area communities. Now, after finishing phase 1 in 2010, there was no budget to continue phase 2. So intro work, filling the gap, doing an impact assessment of floodplain irrigation system in Sudan, and establishing flood season monitoring activity. Knowledge-based development and web-based communication platform was one part of it. Flood season monitoring, which was started in 2010, it was started with objective of having regional collaboration and improving national capacity in mitigation and forecasting of flood. It was very successful program. It's run for the past 10 years. Intro conduct flood forecasting every flood season from mid of June up to mid of September. We engage young professionals from Ministry of Ethiopia, Sudan, South Sudan, sitting here in Intro in Forecast Center and doing forecast. We conduct different flood-prone areas in Lake Tana and Gambela floodplain in Ethiopia, and Barakobo-Sobat in the South Sudan Basin, and in Blue Nile and Main Nile for Sudan river system. So in general, the flood season monitoring program have helped us to have a regional cooperation and conducting those activities. So what we do in this program, we forecast daily rainfall for entire Eastern Nile Basin, which gives 3 days ahead rainfall per day. We forecast rainfall and flow forecast for Lake Tana flood-prone areas, and in Sudan and Barakobo-Sobat Basin. Then, due to different gaps in the previous system, Intro secured some funding from the bank and work in enhancing the previous system to have one integrated forecasting system. And we also work in replicating this kind of forecast system to other sub-basins, which was not covered before, like Tagazet Atbara. Up to now, we never address flash flood in the basin, so we want to start what's happening regarding flash flood. So we did a flash flood assessment, and a web-based early warning system was done, and we want to update our stakeholder, see what are the different key stakeholders in the basin. So we did a stakeholder mapping. So for enhancing the forecasting system, we have developed a rainfall forecast system using a WRF model. We verify this forecast. We have 3 domains developed for WRF, and we verify for different gauge stations. And we use that forecast to see the hydrological forecast using MIC modeling suite NAM model. This followed by the hydraulic model MIC 11, and finally having integrated forecasting system which used MIC operation and a web-based system which will be linked to the website and different examination products. Coming to the social survey which we have conducted recently in 2019, we conducted a social survey for Ethiopia, Sudan, and South Sudan. So we did a stakeholder mapping and survey which flood-prone areas, and we also identify actors, country level actors, which agency, and which is more information provider, and which is can be used for information disseminator. And we also try to see what flood affected communities and what kind of communication means is more efficient. So for that, we have 2 major criteria: sharing information, that means like real-time data getting from the countries to have more reliable forecast, and also to disseminate our alerts and warning messages to most needed part of the basin. The other activity we did is we did a flash flood assessment. In that study, what we have conducted is we already schematized the hotspots which are frequently affected by flash flood. And we also developed a kind of conceptual design in order to develop a flash flood forecasting system. Since we only cover riverain forecast up to now, so what will be different if we have a forecasting system to be done for flash flood? Coming to our dissemination end, as moderator already present, we have a portal which is going to be live soon, integrated knowledge portal. In that portal, we have forecast and monitoring part, which integrate the flood forecast, riverain forecast, and drought forecast. So focusing on the forecast part, we have included the rainfall forecast and flow forecast, which can give live information, giving user different forecast products for rainfall and for flow at various locations of the basin, which we conduct flood forecast. Beside this portal, we also communicate our forecast result to our users through email. And when flood level becomes more critical, we also communicate them by text and also by phone. In the last flood season, I remember we communicated with social media also, especially for Sudan, since WhatsApp is very famous. We have been communicated different warning messages through Nile WhatsApp group through WhatsApp. And at various stages of the project, we have been conducting different awareness and capacity building activity. Up to now, we have conducted 3 flood forums, which have created an enormous platform for networking and assessing what kind of flood-related issue in the basin, how the stakeholders want to be address flooding. We have conducted validation and workshops to get feedback on to our products. We also did lots of stakeholder mapping to see who is more key role player in this area. We have given a lot of training on latest models which we use for the forecast, hands-on training at national level for different forecast users in the ministries and meteorologists. Now, going ahead, we have, through our consultation with our stakeholder, we have identified different areas which still needs our work to have more robust and more efficient forecasting system, which really helps the communities. We know that we have controlled more than 2 million people through our system, but we want to do more. So we have identified 3 areas, the first one being data and model. So we have seen that there's a need to have a ground truthing data to have more efficient and reliable results, to improve our quality of result, and also to ensure trust from our stakeholders. So having a cross-section data, giving a survey or collecting real-time data, and having a kind of MOU with data provider and keeping in place data sharing agreement with the countries will be one of the key areas which we are hoping to work for the future. The second point being software and IT related. Up to now, we have the rainfall forecast and the MikeSuits forecasting system, which was done internally in the server at Intro. But we have been facing a lot of challenge. There are some days which we don't forecast, which is not reliable because flood can't wait for us. So due to different reasons like internet connectivity, power disruption in Ethiopia, and capacity of our forecasting IT infrastructures are the major ones. So moving ahead, we are planning to move our forecasting system to the cloud, which will give us more reliable results. Then the other one, the third one, is having industrial arrangement and communication chain. So to do that, we are planning to strengthen the National Forecast Center, establishing a program in each of the Eastern Nile forecast units, and to have a memorandum of understanding from meteorology and from the ministries to have real-time real-time data access, ensure community and inform timely is one of the areas we are hoping to do. And also having different campaign to raise awareness to the communities about flooding and how to move away from flooding. So from the next phase funding of the World Bank, we are planning to do flood risk mitigation. It's not full-fledged flood risk mitigation, but touching on the soft area like strengthening our forecast system with ground data and establishing a forecast center to the Eastern Nile country. Up to now, only Ethiopia and Sudan have kind of forecasting center, but it also needs strengthening that. And to have a quick response from flooding and assessing people at risk at community level is also one of the areas we are planning to do for the coming 3 years. And finally, having more visibility and by producing our warning and alert communication part in different ways so that people really get our message and use it to escape from flooding. Thank you very much. Moderator, back to you. I'm done.
Thank you very much, Azeb, our expert from Intro. Thank you for this excellent presentation. And thank you for sharing with us this experience, the long experience of Intro in the flood forecasting in the Eastern Nile. Thank you very much. Patrick, can you kindly prepare the presentation for Dr. Muhammad? And in the meantime, can you please, for all our participants, can you type your name, affiliation, and country of residence in the chat room so that other participants can know who's present? Also, please use the chat room to share even like some ideas and exchange ideas. You can also post questions for the panelists and the speakers in the Q&A feature. This will be responded to by the resource persons later. Thank you. Now we are going to our next presentation. It is by Dr. Muhammad Mustafa, and it is about satellite-based rainfall estimation over Sudan. Thank you very much. Please kindly introduce yourself, and the floor is yours, Dr. Muhammad. Welcome. Yes, Dr. Muhammad, are you there? Unmute yourself, please.
Okay, thank you very much, Dr.
Yes.
Mudassir, for your kind words. I am Muhammad Mustafa Abbas. I am working for Ministry of Irrigation and Water Resources in Sudan as a chief engineer. My presentation will go under the title Satellite-Based Rainfall Estimation over Sudan. So next slide, please. Can we move to the next slide? Hello?
Next, Patrick. Yes.
Yeah. My presentation contains some background information about our case study and the objective of this study and the use methodology and the analysis that have been done and the recommendation regarding the analysis that have been achieved and some recommendation have been raised. Next, Patrick. Yes. Actually, the satellite rainfall data have many applications for the hydrologist and for the climatology and biochemical modeling, as well as in hydrology and agricultural meteorology. The satellite rainfall data are is very important for the hydrological analysis, and it is the main input. The rainfall data is the main input for the analysis of the hydrology, and it can be getting from the different kind of different satellite, such as from the World Water and Climate Atlas and the Climate Research Unit. Here we will focus our data gathered from the climate forecast system analysis. And to overcome the problem of the missing the ground rainfall data and to improve the temporary and special resolution of our data, we should look to other source or the available alternatives. So please, the next slide, Patrick. Yes, the main objective of this study is to evaluate the satellite-based rainfall estimations that have been reached, and to predict stream flow that by using rainfall runoff relationship, so we can get the discharge at a selected areas or a selected station. Next, Patrick, please. Also, there is other objective that can be that have been reached during this study, is that and to develop a new methodology for obtaining Basin weather rainfall data, especially over the Blue Nile Basin, as well as to identify the areas of cooperation between the Blue Nile River Basin. We focus here in our this study at the eastern part, mainly the Blue Nile River Basin, and we use the main tributaries of the Blue Nile River Basin, which is about 14 sub-basin, regarding from the Tana sub-basin till we cross the border of the Sudanese area, and we include the Rahat sub-basin and Didi sub-basin, and we make this the 16 together to compromise the total discharge that will reach at Khartoum station. So we can move to the next slide, please, Patrick. Yes. Here is the methodology that have been used in this study. Our data collected is from the climate forecast system reanalysis for the period 1980 till 2010. From the climate, as I mentioned, climate forecast system reanalysis. Then we used modification or adjustment of this data with the actual measured rainfall data from the near stations for the period 1993 till 1999, because this is the availability of the data for this for the research period. And by using weighting factor depending on the distance between the satellites nodes, then we can select a model that we to achieve the runoff at the selected station. We use the WEAP model, water evaluation and planning model, and make some simulation regarding this model for the selected search period 1980 till 2010, and get the analysis and finally the recommendation. Next project, please. Yes, here in this table We have the 16th sub basin in the Ethiopian plateau. Actually, for each sub-basin, we assume that we downloaded the satellite rainfall data nearest the nearest of the middle of each sub-basin. Then we can get its latitude and longitude, the equivalent of this station node, and the elevation to it. The map at the bottom right represent the actual measured rainfall station in the Ethiopian in the Nile Basin. It is about 9 ground rainfall station for the selected period, that is from 1993 till 1999. This is the availability of data for this period. Next, please, Patrick.
Can you speak louder, Dr. Muhammad?
Okay. Thank you, Mudassir. And after that, when we get the rainfall, satellite rainfall data for each of these 16 sub-basin, and we make the adjustment with the adjustment for, or calibration with the ground rainfall, measured rainfall data with the 2 nearest ground station for all the 16 sub-basin. Here I just preview the only one sub-basin for the limitation of the slides, and that is for the Tana sub-basin. We compare it with the Gundar ground rainfall station and with the Bahardar ground rainfall station, and we get the efficiency between the gather satellite data with the ground station. For the first one with the Gundar station, it is about 76%. With the other, with the Bahardar, it is also near to that figure. It is 76% of the efficiency of the between the 2 data. Yeah. Next, Patrick, please. Yes. And after making the adjustment of the satellite rainfall data with the ground data, we get the adjusted data, and here this as it is represented in the top figure at the left, the comparison between the satellite rainfall data in Tana sub-basin and the measured data in Bahardar with an efficiency. As you see here, it is raised to and to it reach to about 95%, and from that we get it, or we measure and compare it at 4 different stations with 4 or 3 different type of efficiency that which give a very good result and reliable. So we can use it in the future. Next, Patrick, please. Yeah, when we combine all the as I mentioned that we do all this analysis for the 16 sub-basin. Here just it was for Tana, but it's actually it is for the 16 sub-basin, and we combine all together, and we use the rainfall runoff relationship, so we can make the comparison between the measured discharge at a dam station at the border of the Sudanese Ethiopia station, and we found that a very reliable result with 0.83 as it's seen here, and also make that when adding the tributaries of Dinder River and Rahad River, and we measured or we compare it at Khartoum station, and also we get 75 efficiency between the two. That is, one is the measured discharge at Khartoum, and the other that came from the satellite rainfall data that and then we use it rainfall runoff. Actually, there's a lot of component in this relationship rather than rainfall only, but here we concentrated only about the rainfall, the data that get captured from the satellite or weather station. Next slide, please. Finally, we get to our recommendation that this result show that utilizing and adjusting the climate forecast system reanalysis precipitation data for the Blue Nile River Basin will provide stream discharges that are as good or better than using traditional weather gauging station. The modified satellite rainfall data represent the ground station in a very without depending on the representative measure data. Finally, development of a network monitoring system for the all hydrological parameter in the basin is very is highly recommended for a high reliable data, and for more, and we are looking for more efficiency rather than that by a cooperation between upstream and downstream countries, and to involve some data in this area. And finally, I can at the end I can say that what you learned at the end of this presentation, that the paper identifies the area for cooperation through a set of a transboundary water resources management system, and the paper also provides the knowledge of the satellite rainfall data and how it can help to solve the shortage of data exchange. Thank you very much, Dr. Mudassir, and all other, and welcome for any other comment or clarification.
Thank you very much, Dr. Muhammad, for this nice presentation about satellite-based rainfall estimation over Sudan, and how you conducted this study in like 16 stations. Thank you very much. Please kindly stay with us. We will have questions at the end of this session. I would like to remind our participant to kindly type your name, affiliation, and country of residence in the chat room, so that other participants can know who's present. And also, please, you can use the chat room to share and exchange ideas also. And you can post your question also in Q&A feature. This will be responded to by the resource persons. Thank you very much. Now we will go to our next presentation by Dr. Kim from WMO. And the presentation is about WMO activities on flood forecasting and management. Dr. Kim, please kindly introduce yourself first, and the floor is yours. You are welcome.
Thank you so much, Mr. Chair. I'd like to share my screen. Hope everybody can see my presentations.
Yes.
Thank you. Hello, everyone.
Introduce yourself.
Yes. Hello, everyone. I'm Hyrin Kim, Head of Hydrological and Water Resources Services Division in WMO Secretariat. And today, I'm in charge of flood forecasting and water resources management. And also I'm working with the drought forecasting and seasonal forecasting, all related to what hydrological forecasting and water resources management part is on our division's work. And today I was given just 10 minutes. So I will just briefly introduce WMO initiatives related to the flood forecasting and disaster measures. Sorry, I will share another slide because it is stuck with me. Please wait. Let me try again.
Okay. Yes. You can put in a slideshow mode.
Yeah,
yes.
I'm trying to do the slideshow mode, but it seems like not working properly. Let me try again.
Okay.
Is it working?
Not yet. Not yet. The slideshow mode, it is below on the left, like bottom corner, close to that. Yes.
Yes, I know. Actually, I'm using F5 function usually, but this time it shows different way. I don't know why it doesn't work well, but let me try. Because I can see the slideshow in my screen, but you still cannot see it, right?
We can see, but it is small. It is not like full extent, and we can see behind your email. So yeah. Okay, now it is better.
Okay. So
yes.
Is it the slide that you can see what will be present?
Yes,
the
we
second
can see.
slide. Okay, so
yes,
I will briefly introduce, thank you, WMO and hydrological forecasting activities and associate program on flood management and integrate flood management help desk, and I will show you community of practice for flood forecasting. Can you see the slide 3? This is World Meteorological Organization, which was set up 1950. And we are trying to support in the technical services to our 193 member states.
You are still in slide 2.
Yeah, that's why I'm. It's very strange. Okay, I will just go using another.
Now yes,
okay.
now you are in slide 3. Thank you.
Okay, thank you so much. So I will skip. Majorly, WMO is a specialized agency for the weather, climate, and operational hydrology. I will just skip to the number 5, slide 5. That I already shared my slides, so everybody can receive the slide if you need it after the forum. So the major application for the operational hydrology to development issues, including water management, agriculture, policy formulations, and also disaster prevention and mitigation. And we also encourage research and training. We also promote the rapid exchange of data information, and we also promote standardization of observation and also ensure the uniform publication of observation and statistics. I don't know you are familiar with the WMO new structures, because we have been restructuring WMO governance, and it's more broader than this, but I wanted to highlight hydrology within the WMO structure. So as you can see, we have a regional association, RA1, 2, 3, 4, 5, 6, with 193 member states. So in especially Nile Basin is working in the RA1, Africa Regional Association. And we have Executive Council, Technical Coordination Committee. And here in the Congress, now we have a Hydrological Assembly. At the same time, whenever WMO Congress is held, we will also have the Hydrological Assembly, which is consists of the National Hydrological Advisors. So during the Congress, we also have a special time to discuss the hydrological related matters. And then we also have a hydrological coordination panel here. So they are the think tank of WMO in hydrology, because in hydrological services is Standing Committee Hydrological Services stays under the Services Commission, and other things like observation, measurement part, monitoring part is under the Infrastructure Commission now. And especially we have expert team on hydrological monitoring under the 3 standing committees. It is a joint expert team. And also we have a hydrological services. We also support the research board. So now the hydrological coordination is very important to cooperate with all other bodies, constitute an expert team and technical commissions. Also, hydrological coordination panel is working with the other external water bodies, including private sectors, NGOs, research part, and the UN other agencies as well. So this is some highlights in the Congress Resolution 25th that we have major hydrological initiatives from the one quality management framework. And I especially wanted to highlight the WMO flood forecasting initiatives and hydrological contribution to disaster risk management. So that is our highlights for the major hydrological initiatives. This is one of our activities in WMO, which we called Flood Forecasting Initiative, FFI. Under the FFI, we have been developing assessment guidelines, which will be finalized soon. And it is including evaluation of national services capacity building capacities. So this, if you're using this assessment guidelines, the members and the National Hydrological Services, they can do self-assessment by themselves, or we can support our experts to assessment together to find the gaps and how we can increase or support to improve the National Hydrological Services. And we also preparing interoperable platforms and models. Now we have a standing committee hydrology who are working for developing the community of practice for flood forecasting. And in this website, we will show some index. We will show some table with available tools, available modules, available platforms, which is freely available to everyone. And we have some category to fill. So if they fill the most categories, then WMO can recommend it to the consideration for their for the using, and also implement to the members. And we also will have some training programs for members, and with all of that it is a strength. It will be strength the flood forecasting chain, value chain, that we believe. And in the inventory of the interoperable models and platforms, that as I mentioned about some categories, that it is the must be category, the operational use, and be freely available, and very low hardware requirements, because if it is the case, very high technique like a supercomputer, it might be difficult to the members using those software. So we have a certain category that it should be also available in one of the official UN languages, and it should have some training materials. And sustainability is very important too, and the institutional support as well. So those categories that if the models platform is can pass the must category, they can be the part of inventory of the interoperable models and platform. And we think that it is very important to have the interoperability, because we can see many times that some special models systems cannot adjust it to the existing system. It is not the sustainability. So we want to have interoperability, which is available, and availability to put in the model or software, automatically exchange and make use of information from one to another. That in that context, if you already have like a MIC 11 or other forecasting systems, that if you want to use another tools, that it will be easy to interoperate. So you don't need to develop from the very beginning. You can use your existing system with other tools. That will be very helpful to the Nile Basin members, as I think. And this is our ongoing project, which is we have multiple donors that providing funding to implementation for supporting the flood forecasting or water resources management, etc. So this is for the further developed services in support of sustainable water management. So far in our division, Hydrological and Water Resources Services Division, that we are currently covering 90 members. In RA1 Africa, we are working in the project 28 members and ongoing, especially for the Southern Africa, West Africa, and also Lake Victoria as a pilot studies. Unfortunately, I couldn't see many of the activities ongoing with the Nile Basin, river and country, but I believe we have a chance to develop proposal or future activity together with your strong engagement. This is one of our activities that we have been implemented more than 60 countries, which is an ongoing project with multiple donors by USAID and CRUISE. Then over than 3 billion people around the world that having to implement this FFG flash flood guidance systems. And the other ones that we also have Mythological, which is applying for the Volta Basin flood and drought management. And this is for more than 10 countries so far. Mythological has been implemented. And we also have associated program on flood management, which we call the APFM. And this is a joint activity between WMO and Global Water Partnerships. So this is trying to make some concept of integrated flood management. And you can just click the website, www.floodmanagement.info. There is many available tools and guidelines that you can find here. And we also have integrated flood management help desk. So far, we received 425 requests, and it is average 38 per year. And mostly it is for the capacity building, or it is about the major governance, and anyone can just visit our help desk and ask some support. It is possible that you can ask some training, or you ask some technical support, or you can ask to have a new project together, because we have more than 30 plus support-based partners in this help desk, which we called IFM, the support-based partners. So they are willing to support technically, in-kind contribution, and also develop proposal together, which I mentioned about Volta Basin flood and drought management project. This is one of our research that support base partner working together and develop the proposals and making available from the donor, which was the Climate Adaptation Fund, and started the real implementation project in the Volta Basin. So this is one of a success story. So you can just visit the help desk if you need any requests or support that we are willing to support. We are willing to help and working together closely with our support-based partners. So as you can see, preparation of a project proposal or supervisions of technical implementation, capacity building, training, there is no limit if it's related to the flood management, flood forecasting. We are happy to support all the levels. And it is not only for the government agency, but it is also including other agencies like research or academia, NGOs, university. It is open for everyone. This is our AFM integrate flood management, more than 30 support-based partners. And Deltares DHI, as you can see, they're one of our support-based partners. And we also having more and more support-based partners. So now recently Caritas, the Swiss agency, and also Water Use Network, IUCN, become our new export-based partners. And this is about that we are working and developed of the community of practice on our end-to-end early warning system for flood forecasting. So this whole value chain, as you know, flood forecasting is not just for the modeling, not just for the hydrological modeling, not just for the climate or meteorological forecasting. It has to start from real-time data collection, monitoring, and also data quality control, and including model forecasting and dissemination of early warnings. And it is including decision support. And after the disaster, it also needs to have the response to warnings. So we have to have all the feedback and review. So I believe in this coming July that we will have a forum and community of practice website, which is available in the flood management info website. So this community of practice website will have, as I mentioned, the assessment guidelines, inventory of the models and platform, and all the hydrological forecaster, flood forecaster, they can join this website, share their experience, ask each other, finding materials there. So I hope this community of practice is well distributed and hope to use as one of the great opportunity to make a forecasting communities. And it is my last slide, but I also wanted to highlight, as I see the keynote speech that mentioning about drought forecasting and also seasonal forecasting, because April 6th, during this forum, that we will have another presentation for the Hydro SOS, which is WMO, one of the WMO major initiatives, hydro status and outlooks. This is for the seasonal forecasting. And the thing is that Hydro SOS do not just provide or recommend one specific model or tools or platform. No, if there is a multiple available for the seasonal, sub-seasonal forecasting and monitoring, that it is freely available, we are welcome to be part of Hydro SOS. So I also want to participants to consider to join the 6th April to know more about Hydro SOS as well. Thank you. That's all for my presentation. Thank you very much for your attention.
Thank you. Thank you very much, Dr. Kim, for this excellent presentation. And thank you very much for telling us the opportunities that we have at the WMO, and that you have like this also hydrological services also at the WMO, and you have a lot of work also related to the flood forecasting. And also you told us about the opportunities for collaboration and also support by the WMO. Thank you very much. Please kindly stay with us. You may have some questions by the end of this session. Thank you, Dr. Kim. Now we will move to our next presentation. It is by Dr. Christian. His presentation is about monitoring water levels and reservoir from space. Please kindly introduce yourself first, Dr. Christian, and the floor is yours. You are welcome.
Thank you very much. Can you see my presentation in presentation mode?
Yes.
Okay.
Thank you.
Thank you. My name is Christian Schwadke. I'm from the Deutsche Geologische Forschungsinstitut of the Technical University Munich, Germany. And I'm working there as research associate since more than 10 years in the field of satellite altimetry. And this is also the topic about my presentation today. So I will talk about the monitoring of water levels of the Nile River and its reservoirs by using satellite altimetry. First, I would like to start with a short motivation why we are doing this. So there are the monitoring and the modeling of the Earth's water cycle has become increasingly important in the last years, especially in the context of climate change. That's the one point. And on the other side, the number of in situ stations are declining worldwide since 1980, which can be seen on the right figure, which is the statistics of the global runoff data center. So we see a strong decrease in situ data for monitoring the water cycle. And there plays the satellite altimetry a role because it has the potential to monitor the water level changes of river, lakes, reservoirs, and wetlands, also in remote areas where we don't have any in situ data. And at our institute, we have developed a database called Database for Hydrological Time Series of Inland Waters called Tahiti. And this database provides now more than 3,000 water level time series derived from satellite altimetry and other hydrological products such as surface areas and remote volume changes, which are derived from remote sending satellites. And in this presentation, I will now demonstrate the potential of satellite altimetry to monitor the water level changes of the Nile River and its reservoirs. First, I would like to give a short introduction to the satellite altimetry and how water levels can be derived. So, satellite altimetry was originally designed for measuring the sea level in the ocean, which is possible since the 1992. But for more than 2 decades now, satellite altimetry can also be used for the monitoring of inland water bodies. And the measurement technique of satellite altimetry is the following. You can see in the figure on the right the satellite, which has an altimeter there, and in this the measurement techniques emits a radar impulse which goes down to the sea surface, or the water surface, is reflected in and travels back. And so the measurement technique of satellite altimetry is to estimate the runtime of the signal. Unfortunately, this technique works only in another direction, which means that the satellite has to cross the inland water body of interest directly. And so it is not possible to capture all inland water body of interest. The range we achieve from the measurement has then to be corrected by geophysical corrections, such as the troposphere, and also we apply a geoid model to this range in order to get autometric heights, which can then be compared, for example, with in situ data and can be introduced into any models. And in our approach, which we have developed at our institute, the Tahiti approach, there we derive the water level time series based on an individual analysis of the radar echo. So it means that we analyze the echoes by ourselves, called retracking. And so we derive our own range and apply an extended outlier rejection on the data. So because not all reflections are located over water, or some reflections are affected by land around. So this has to be rejected first. And afterwards, we apply a Kalman filtering on our data to estimate the water level time series. As input data, we use cross-calibrated multi-mission altimeter data. So that means because we would like to merge different altimeter missions, and to avoid intermission offsets in the water level, we made a cross-calibration so we can use all missions which are available to use it as a kind of a single altimeter system. And the water levels we achieve and compute have a accuracy which depends on the one hand side on the size of the shape of the water body, but also on the quality of the used altimeter mission. So the larger the water body is, the better is the resulting time series. And also if we use older altimeter missions, the quality is not as good as the new ones which are currently on the orbit. And nowadays one can say that for larger rivers, an accuracy of few centimeters can be achieved, or respectively few decimeters for small rivers and small lakes. So we have the possibility to observe and monitor rivers which have a river width of about 200 meters and lakes which have an area of about 5 square kilometers. Here now we can see in the next slide an overview of all altimeter missions which have been launched since 1972. And for inland water body application, we can use the mission since 1992, starting with ERS-1. And in this presentation, I will focus on 4 different characteristics, so 4 orbit types. So you can see here in first, the 3 satellites, ERS-2, Envisat and Saral. They all fly on the same orbit and have a repeat cycle of 35 days, which means we get one measurement every 35 days. And on the other hand, it has a track distance at the equator of 80 kilometers. Then we have the second group, that's the Topex Poseidon with adjacent satellites. They have a higher repeat cycle of 10 days, but a lower track distance at the equator. So there's a compromise between the repeat cycle and the track distance. So you will see more about this in the next slide. Then we have the Sentinel-3A, which are very new satellites, and 3B. They are identical, but the Sentinel-3B satellite flies in an interleaved orbit to satellite 3A. Now we come to our study area, which is the Nile Basin. So there's the Nile with the rivers, so the Nile, the Blue Nile, the White Nile, and also the different reservoirs like the Nasser, Osiris, and the others. And here now you can see an example how the tracks are located on over the lake. Here you can see a small section of the Nile. You can see clearly here the Nile itself. And you now see the different altimeter tracks which are crossing the river. So you can see in red, for example, the Jason and Topex satellite tracks, which are only few tracks. That means because they have a high repeat cycle of 10 days, we have less tracks available where we can observe the water levels. On the other hand, if you look on the Envisat and Saral and ERS tracks, there in blue we have much more data, but therefore a lower temporal resolution. And now we have the possibility to estimate one water level time series at each river crossing point, if we want it. Now I will show some results, how they look like. So the first thing is an example here at the White Nile, where we look at the river reach of about 60 kilometers near the city Malakal. There you can see it is crossed by 6 tracks. At the beginning we have 2 Sentinel-AB tracks. At the end also, and in the middle we have a Envisat and Saral track. The resulting time series looks as follows. We can see nicely here in blue and red the time series of the first Sentinel-3A and B crossings. In orange and brown we can see the crossings of the last one, and in the middle we can see the time series of the Envisat and Saral time series. Every time series shows a very nice seasonal variation, a good agreement, and you also can see that there are offsets between the different time series which are related to the river slope. So you can also use this and derive this information from satellite altimetry in order to feed your river models and your monitoring systems to use this information. Maybe, for example, if you are estimating river discharge or something. Now we look at the largest reservoir at the Nile, the Nasser Lake. This has about 5,000 square kilometers, and this is crossed by 15 altimeter tracks, which you can see here in the image. There are all satellites I showed before available. And now if we combine all the data, because as I said, we use altimetric heights, so we can merge all the different altimeter tracks together in order to derive one long-term water level time series of this the reservoir. And here you can see very nice a time series since 1992, and which shows very nice the seasonal variation and also the trends in the reservoir. And what you also can see is that we get more and more measurement points until today, because we have more satellites in orbit and more information available. So that means that we can also increase the final temporal resolution down to a few days for the time series by combining many as possible altimeter tracks. Now we look at a smaller reservoir, the Reservoir at the Blue Nile. It has only 290 square kilometer, which is only crossed by 3 altimeter tracks, which you can see here. So it's one NVSAT track with Saral and ES2, and the 2 Sentinel tracks here in the middle. And if you look here on the time series, you can nicely see again here the time series since 1996 until today. We can nicely see the seasonal variations, and we can also see this jump here in 2013, when the dam was increased by 10 meters, and you can also see the time series afterwards, on which the water level is much higher. Now I come to my last example, that we not only can observe the water level of the reservoirs, but also at the outflow. Let's say here, for example, we see in the bottom the Osiris Reservoir, and 50 kilometers downwards we have 2 Sentinel tracks crossing the Blue Nile, where we can derive 3 water level time series, because 1 altimeter track crosses the Nile twice. And this is very nice, because we can see it here on the water level time series, that the measurement, the water level time series here in green and blue are measured at the same time. So we can use this information additionally to make a quality assessment of the time series, because we don't have, if you don't have any in situ data. And it shows that there have a very high correlation and a very good agreement between both time series, and we can immediately also estimate the river slope for this river segment. Overall, if we look at all the 3 time series, we can see again very nicely the clear seasonal signal of the Blue Nile. Now I come to my conclusion. As I showed, satellite altimetry has the potential to monitor water level changes of the Nile in its reservoirs, and it's a valuable data set to monitor especially inland waters in remote areas where we don't have any in situ data available. And additionally, the water level time series in Tahiti are also provided, as I would say, near real time, because it depends on the data availability. So the data of the time series will be updated continuously. But as you know, depending on the temporal resolution, it can take more than 35 days until a new measurement is available. And so I would like to conclude with this information. And if you need more information about the Tahiti and our processing, feel free to visit our website. Thank you.
Thank you. Thank you very much for this excellent presentation, Dr. Christian, about monitoring water levels and reservoirs from space. And you gave us some nice examples about some reservoirs along the White Nile, And also you showed us your experience of monitoring also the water level on the Osiris and how it captured very well after the heightening of Osiris, the new water level like heights. Thank you very much for this nice presentation. Please stay with us. You have some questions. We will post them to you by the end of the presentations. Thank you.
Thank you.
Now we are moving to Dr. Hussein from ECPAC. His presentation is about ECPAC precipitation prediction over the Great Horn of Africa. Dr. Hussein, please kindly introduce yourself first, and the floor is yours. You are welcome.
Thank you, Dr. Mudatir. My name is Hussein. I am a climate modeling expert at ECPAC. My presentation is on the ECPAC precipitation prediction over the Greater Horn of Africa. So mainly my presentation will focus on the tools we use and also the practice that we produce for different time scale. Just briefly about ECPAC. ECPAC stands for IGAD Climate Prediction and Application Center. The center is established in 1989 as a drought monitoring center. Then in 2007, the protocol established and the name changed to IGAD Climate Prediction and Application Center. In May 2017, ECPAC was designated as a WMO Regional Climate Center for the Eastern Africa. ECPAC is a member of the AUC NEPAD network for water centers of excellence. ECPAC has also got an observer status with the UNFCCC. So the main mission of ECPAC is to foster climate service and knowledge to enhance community resilience for the prosperity of the Greater Horn of Africa region. So we are serving 11 countries, 8 IGAD member countries and 3 non-IGAD member countries. When you come to the tools and the products that we develop at ECPAC, we use 2 approaches to produce precipitation forecasts. One is the dynamical downscaling and the other one is the statistical downscaling. For the dynamical downscaling, we use the WRF model, which is weather research forecasting model, a regional climate model. And using that model, we produce weekly forecasts, and also we also produce a tropical cyclone track when it occurs over the tropical Indian Ocean. And also we produce intra-seasonal rainfall characteristics, like the onset, the wet spell, dry spells for the different rainfall seasons. For the dynamical downscaling, we use 2 approaches. One is called a local regression, and the other one is we use the climate predictability tool, which is uses the canonical correlation analysis. So using these 2 methods, we produce the monthly rainfall outlook, seasonal rainfall outlooks. Then we objectively combine the outputs from the 2 different techniques and got different products for the different months and also seasons. So those products includes the tercile probabilities, ensemble mean, and also anomalies, probability of exceedance. We are currently also developing some products which indicates a drought using the standardized precipitation index. So as I mentioned, the dynamical downscaling is using the a WRF model. And for this model, we use initial and boundary conditions from the NCEP CFS V2. And we run the model every week to produce the weekly forecasts and to produce the other intra-seasonal rainfall characteristics for the different rainfall season. We run the model at the beginning of the rainfall season. So for East Africa, we have 3 main rainfall seasons: the March, April, May, June, July, August, September, and October, November, December. So for those different rainfall season, we run work for the season. For the season, then we produce the intra-seasonal rainfall characteristics. For the tropical cyclone part, we only run it once we see a tropical cyclone start developing over the nearby oceans or seas. So once we see a development of tropical cyclone over the Indian Ocean or the Arabian Sea, then we run the model to track the path of the cyclone. These are just some of the products that I have mentioned. So for the weekly one, we produce this weekly total rainfall for the region. This is just a forecast for this week for 23rd March to 30 March 2021. And the right, it shows the heavy, very heavy and extreme heavy rainfall areas that receive. So the heavy rainfall is defined the 90th percentile, and the very heavy is 95th percentile, and then the exceptional or the extremely heavy rainfall is the 99th percentile. So for this week, we don't see much extreme rainfall. It's only showing over the parts of Tanzania, southern and the eastern part. But if you look at other weeks, this is just on the past for December. So you can see that most areas of the Greater Horn of Africa are expected to receive those extreme and heavy rainfalls. These are just some of the examples of the tropical cyclone forecast that we produced on the past. This on the left shows the Makweni, which occurred in 2008, and the KR over the Arabian Sea in 2019. So this is some of the products that we develop once we observe a tropical cyclone development over the Indian Ocean. For the within season rainfall characteristics that I mentioned, so like the onset of the rainfall. So on the left, it was the forecast for October, November, December for 2020 for the previous OND season. Then we compare it with the climatological onset, and then we indicate whether the onset will be late or early with reference to the climatological period. So these are just some of the products that we produce using the dynamical downscaling techniques. We also produce other products like the subseasonal products. These are not publicly available because the data that we got is not it's not publicly available. So we produce and share those products only for a specific groups. For the statistical downscaling approach, we use 10 global climate models. Many of them are from the North American multimodal ensemble, and we use some European models from the Copernicus data portal. And this data sets processed every month, and we produce the monthly and seasonal outlook for the region. So as I mentioned, we use two techniques like the CPT, which we uses the canonical correlation analysis, which mainly accounts the large scale features like the impacts of the ENSO and the Indian Ocean dipole. The other approach is the grid point linear regression, which is based on the R script, and it accounts the model dynamics and also the large scale features. So finally, we got those, we use those two approaches, then we just do equal weighted average to develop the consolidated forecast. So this is how we produce it. So we have different models. They have like 10 models here. Then you have, we use one technique and produce the probabilistic or the anomalies using the regression technique. Then using the CPT tool, which uses the canonical correlation analysis, then we produce again the forecast using this technique. Then finally, then we just average the outputs from the two techniques and get the average forecast. So once we get the average forecast, then finally we average them, then get the consolidated forecast. Then not only the forecast, but we also look at the skill of the models for using each approach for the different rainfall seasons. This is just an example of the correlation score for the different models. So we have the raw correlation on the top, then we have the cross-validated one from the regression technique and from the canonical correlation on the last one. So this is using the two techniques. Yeah, we have the average of the regression. We have the average of the forecast from the canonical correlation analysis. And finally, the objective outlook looks like this one. So it is the average of all models and all techniques. In addition to what I mentioned, we also produce a probability of exceedance, certain threshold for the particular month and particular season. This is again another example which shows areas that receive the probability that some areas receiving 250 millimeter, and what is the probability exceeding 300 millimeter, and what is the probability 350 millimeter. So here we can choose the different threshold depending on the season. So these are just examples. So in this example, this is now the probability exceeding the 200 millimeter rainfall for that particular season. So then when you choose higher threshold, then you will get very few areas that are expected to receive above like 350 millimeter. So these are just some of the products that we produce at ICPAC, focusing on rainfall. But we also produce other products. So if you want to know like the products that and also the areas of work at ICPAC, maybe you can go to the ICPAC website and go to the products and look at the different products that you are interested in. In addition, if you want to receive the products on a regular basis, you can just sign up, click here and sign up. Then once you register, then you will get the products on a regular basis. This is my last slide. So thank you very much for giving us the opportunity and make a presentation on this forum. If there are any questions, I'm happy to take. Thank you. Over to you.
Thank you. Thank you very much, Dr. Hussein, for this excellent presentation about ICPAC forecasting and about ICPAC products, and also the possibility of getting some other detailed products and the different methods you are using to produce your forecast and the area of your forecast. Thank you for sharing this valuable information with us. Please kindly stay with us. Now we are moving to our next presentation. It is by Dr. Hubert. It is about big data, trends in data acquisition and data exchange between countries. Thank you.
So thank you very much, Dr. Mutadir, for your kind introduction. So this is my second presentation, so I skip my introduction about my person and I directly start with the big data presentation, trends in data acquisition and data exchange between countries. It is kind of a follow-up of what was presented by Mr. Christian Schwadke from the University of Munich, but not 100% continuation, but part of my presentation take on the approach that was introduced by Christian Schwadke. In recent years, we can say that hydrology has embarked to a new area, which is supported by more and more advanced computing power, and internet applications. And this is why big data has arrived in many fields of work, also in hydrology, but not only in hydrology. And this is this is why we have started also looking into opportunities with big data approaches. So what is big data? What we need is a definition about big data to better understand what we are talking about. You see four, let's say, terms: volume, velocity, variety, veracity. These are the four principles which define big data. Volume is about the huge amount of data that is produced. Velocity is the speed at which data is processed and eventually used. Variety is the wide range of possible applications. And veracity is simply that data must be representative and realistic. And what you see is, for example, in the veracity here from the WMO, the presentation of monthly temperatures year by year, and now you see how the temperature increases year by year, and the recent years were by far the warmest. So this is just one nice example of big data applications. So the core elements of big data are automation. Given the huge volume of data, it is a must that we apply automated processes. It cannot be done manually. The volume of data is growing permanently, and what is absolutely essential is that information must be somehow filtered, prepared, in order to make it accessible and understandable. In other words, we need a proper presentation layer. Otherwise, we get completely lost in the stream of new data. So big data in the water sector. Here an example of the Nile DSS that is in operation at the Nile Secretariat. And satellite data here is used and updated and incorporated in different processes. Please remember the keynote speech presented by Dr. Mutadir and also the presentation of Asep Mersha from Entro. They both explained, not mentioning the term big data, but what they do in the background is they make use of big data actually. They update models, they calculate various hydrological parameters within the Nile DSS, and they also facilitate monitoring and forecasts. And that is also all is in progress at the Nile Secretariat. Then, when it comes to, let's say, number crunching, that is the data sets that grow steadily, and that is the number crunching part. And that is all about modeling and calculation. And that all the models, they consume the data and transform them into something new, easier to digest information. And finally, we need the presentation layer. And we have to filter the information in order to produce results that can be understood easily. And this is actually a very difficult task. You can imagine to consolidate the amount of data that arrives every day, growing, and to prepare that is not that easy. And it must be prepared so that, let's say, decision makers can get the information in a way that it's a real answer and not so complicated that they just struggle with the information. Though that is really a challenging topic to present or to create a really good presentation layer. So what can we say? What is a traditional way of data exchange and data use? First, it is to run an operational monitoring system. And that monitoring system, a hydrometeorological observation network, data is recorded, transmitted to a server, and from there maybe data is disseminated further to users. So we have this chain from monitoring, data exchange to data use. With big data, it looks a bit different. Almost everything has its origin in satellite data. And from there, we get, for example, rainfall estimates, and for example, satellite altimetry, which was introduced by Christian Schwadke, and we get many more other parameters. The next layer, and I call that, or a next possible layer that comes into play is, I call it large-scale modeling. This is mainly driven by satellite data and usually developed without information on the ground. I will show examples later on that topic. And these applications are usually accessible via internet, and there they allow to visit or download and use their data for your own purposes. What can improve the applications, of course, is the input from monitoring system. That means the input from in situ observations. And that is recommended in order to calibrate the big data applications. I would like to show two examples. One, the first, is the streamflow service from the European ECMWF Center. And the second is what you have already seen, the Tahiti satellite altimetry. So first, the ECM streamflow service model. This model is a hydrological one, and it covers the entire globe. And if you look at the map, and in case you were just in front of the internet website from this GeoGlobe's ECMWF service, you can zoom in, and surprisingly, the level of detail is very high. So you can zoom in, and then you see more and more rivers which are captured by this model. Now, what I did for this presentation is I zoomed into the Eastern Nile region and have selected one of the river reaches for this presentation. It's about the Blue Nile LDN station, which is close to the border between Sudan and Ethiopia. What we get for all river reaches, not only for this one, for all river reaches which are covered by this model, we get 6-day forecast consisting of 51 ensemble representations from different satellite rainfall estimates. You can either retrieve the statistics of the forecast, which means you get the median and percentiles for the 51 ensembles, or you can retrieve each of the ensembles by themselves. And another option is to retrieve the long-term simulation streamflow time series for each location. That is good if you want to do the calibration with that model. That means you want to fit that model to your particular purpose. So clicking on one location, it gives you the last calculated streamflow. As you can see, I accessed that site a couple of days ago, and they update that on a daily basis. So let's make it a bit interesting now. And what we see here is the original long-term streamflow time series of the ECMWF model. This is the blue Nile and what you see also is the green line. That is the calibrated model from the Nile DSS toolbox, and that was transformed into the TALSIM NG modeling package. So what you see, and that is obvious, bias correction is absolutely required. So if we do that, because we have this calibrated model at hand, it looks like this. What we get then is we get really a big improvement. the hydrograph is now pretty close, is a pretty close match now with the calibrated streamflow. I click once so that we can see the zoom in. But we have still some differences, but this is maybe possible just to eliminate the differences with a more sophisticated bias correction process. But all in all, I would say comparing the situation before bias correction, now with after bias correction, it looks pretty convincing. And we should not forget this model was developed without any ground observation. So as a conclusion, the large-scale model of ECMWF can be turned into a qualified data set in terms of streamflow if we have information available and at hand to allow us to make a calibration effort and a bias correction steps. So not all, I have to say, not all locations might be as good as this example. I've tested quite a few of the locations, but I can confirm that on average, the results look pretty good and they can always improve, and then they turn out to be absolutely satisfactory if we have data at hand to make a proper bias correction. So if we go further to the Tahiti satellite altimetry, this is what you have seen already in the presentation of Christian Schwadke. He introduced that. It's about the Reservoir dam here and the water level. And due to the heightening of the dam crust, you see here the jump, and that is the situation in 2013 to 2014. Higher water levels are now possible due to the elevated crust level. So that's become clearly visible in the chart. And now let's have a look into details now. And you see this since they changed, since the rehabilitation of the Reservoir dam. I show here the calibrated model Tahiti. That's a reservoir operation model. And you see how well the model, which represents the currently used operation rule and the satellite altimetry match together. Now we can say the comparison is either to confirm the quality of the Tahiti satellite altimetry in terms of the quality of assessing good water levels, but we could also say the other way around. If Tahiti with the water level assessment is a very good approach, we could also say that this confirms the quality of the model and the quality of the operation rules that were implemented into the model. So we have two ways to look at this situation here. The model stops here, what you see in end of 2014. That is where all the information stops at the moment, so we can't provide all the information up to now, but satellite altimetry can, of course, because that simply relies on the satellite information. Another example is Lake Victoria, the water level assessed by the satellite altimetry approach of Tahiti. And then you can see here now this huge rise of the water level, which means the extreme event in 2020 becomes clearly visible and shows, at least as we can see on this slide here, it is somehow an all-time high. If we look further back and we take historic information on the water level, as far as I know, this is not the all-time high, but it's very close to the all-time high. So we are back to a situation which was maybe in which occurred, I don't know exactly, in the 60s of the previous century, possibly. So let me come to the conclusion. What are the opportunities with regards to big data? First, I would say it is about the use of freely available data. Satellite and large-scale models make use of these free data, and they provide itself hydrological relevant information for free. Satellite data in itself is also accessible free of charge, at least as the satellite missions belong to NASA or the European Space Agency. With calibration, or bias correction. The big data applications can be turned into fully qualified data sets. The example was given with the LDM Blue Nile station, where you could see the level of improvement from the original data to the bias corrected data of the streamflow service. And I presented two parameters, water level and flow. You have to bear in mind, two parameters are just an example. I guess probably important parameters from the viewpoint of hydrology, but it's not the whole set of parameters that are available with these big data applications. So as a result, what would I say here in terms of data acquisition and data exchange between countries? Big data do have the potential to enhance hydrological observation networks, especially for remote areas which are difficult to access and difficult to monitor and to make in situ observations. But still, we need some information collected on the ground to enable calibration. Another maybe very interesting aspect is just in terms of data exchange and data exchange agreements. Big data cuts across borders. Big data applications do not stop at border. An interesting fact, especially in terms of data exchange. And finally, I would conclude with the following. It is a recommendation to combine monitoring systems, existing hydrological models. Please remember what Dr. Motadi and Asep Mirsha has presented. And finally, we can fill the gaps and maybe more with the big data applications. If you want to know more, please visit our website. Thank you very much for your attention. I hand over back to Dr. Motadi. Thank you for your attention.
Thank you very much, Dr. Hubert, for this nice presentation about big data and the opportunities we can get in leveraging from this big data. Thank you very much. Please kindly stay with us. Now we are moving to the last presentation. It is by Dr. Christoph. The presentation is about regional seasonal forecasting for the Blue Nile and Takazi-Sitet-Atbara basins. Please kindly introduce yourself first, Dr. Christoph, and the floor is yours. Thank you. You are welcome.
So, thank you very much. Can you see my slide?
Yes, very clear. Thank you.
So, my name is Dr. Christoph Lorenz. I'm a researcher at the Karlsruhe Institute of Technology, but not in Karlsruhe, but in Garmisch-Partenkirchen. And I have to say that the previous presentation by Dr. Lohr was a perfect introduction to our presentation, because he mentioned bias correction is crucial. And this presentation will be about bias correction. As we are already quite late in the session, I think I will skip the main introduction, because I think we all agree that climate change and the rise of population is somehow increasing the water stress, especially at climatic vulnerable or sensitive regions. So we think that the timely and proactive water management is getting more and more crucial. And we also all agree that seasonal forecasts could be the right tool for exactly this kind of timely water management. But as already mentioned in the previous talks, the seasonal forecasts that are available today, they have some issues, some shortcomings. And some well-known issues are that they suffer from model biases. They suffer from a coarse resolution. So they are global models. They usually have a spatial resolution of around 50 kilometers and more. So this is already putting a lot of, let's say, trouble when we try to use this kind of information for the regional water management. So just to give an example here, this on the left-hand side is now the seasonal precipitation sum from the CS5 seasonal forecasting system from ECMWF. And on the right-hand side, you see here kind of the same seasonal precipitation, but from a kind of reference data set. In this case, it's the ERA5 land product, which is also published from ECMWF. We can see that First of all, the precipitation sums are different. So the seasonal precipitation sum from the forecast are lower compared to our reference data set. And we can also see that, of course, the seasonal forecasts, they lack of spatial details. So we see all these very high peaks and small patterns here in this ERA 5 data set, which are absent in the CS5 product. Another problem, which might be even more critical when it comes to impact modeling, to hydrological modeling, are the so-called model drifts. So depending on our issue month or issue date, when our forecast has been issued, we achieve different magnitudes of, for example, precipitation forecasts. So if we, for example, try to forecast the seasonal precipitation with a lead 5 forecast, we can end up with totally different precipitation sums than if we would try to forecast with a lead 5 forecast, for example. So this means that the post-processing of seasonal forecasts is crucial if we want to use this kind of information for the regional water management. And this is what we have done now in the last couple of years. So the product that I would like to present to you is called CS5 BCSD, and this is just to give you a very brief overview about the things that we have done and about the, let's say, key aspects of this kind of research. So the key idea was that we develop a kind of regionalized seasonal ensemble forecast system for several semi-arid river basins across the world. And this has been done within the GROW SAVAM project, which was a research project from a couple of German research institutions. And right now we have now seasonal forecasts for 4 domains across the world, 4 mainly semi-arid domains across the world. And one of these domains also includes the basins of the Blue Nile and the Tekesi-Atbara Basin. So the aim was to develop a kind of bias correction and spatial disaggregation for improving the spatial resolution of the seasonal forecast, to reduce the biases and to in principle, achieve an overall improvement of the raw CS5 forecasts. Another key aspect is that we would like to, or that we want to freely publish all the data that we have produced, so that it can be used for capacity building, for education, and so on. And we also want to implement an operationalization for providing up-to-date seasonal forecasts. And this is something that we have achieved now. And I will go very briefly now about some key details of the CS5 product. So one of the fundamental improvements is, of course, after any kind of bias correction, that we end up with reduced biases, but we also could remove all these drifts, and we, of course, also end up with a higher spatial resolution. So here you see now the same image from before. On the left-hand side, you see the CS5, the raw CS5 forecast. On the right-hand side, you see the reference product from ERA, or the reference precipitation from ERA 5 land. And in the middle, you see now the CS5 BCSD forecast, the seasonal forecasts, the seasonal precipitation sum forecast. And we can see that we have achieved quite a high level of agreement in comparison with this ERA 5 land reference product. We can also look at basin scale forecasts. Now, if we aggregate the precipitation forecasts or temperature forecasts across the whole basins, we can also see a quite significant improvement compared to the raw forecasts. So in particular, the biases of our BCSD forecasts are close to 0 when compared to ERA 5 land. Also, the seasonality of forecasts is substantially reduced. So you could see here in this kind of bias graph, before our bias correction, you could see this kind of dip downward, this downward dip in the biases. So of course, the precipitation biases were highest during the rainy season, and similarly, the temperature biases were quite high. And after applying this kind of BCSD, we end up with almost 0 biases. Another aspect is that we have improved the kind of consistency across our lead times. And this also shows again that we could successfully remove all these drifts and issues of, or at least reduce all these drifts and issues of the seasonal forecast, of the raw forecasts. So let's summarize that this BCSD that we have just applied is a kind of simple but very effective method for reducing biases and model drifts and for achieving kind of consistent seasonal forecasts. More results and more evaluations and performance metrics are shown in this publication, which is hopefully accepted soon. But let's look at some real events, because we can always look at kind of artificial skill scores, but I think even more impressive might be to really show if we were able to forecast some real events. Now we all know that this huge flooding event last year in the rainy season last year was mainly due to very high precipitation amounts, and actually we could see a kind of very wet conditions already in May 2020. So already a couple of months before the start of the rainy season, we could actually see these kind of wet events that might occur during the rainy season. Similarly, I have also included here an example from another study region of the Savam project, which is now here the Karun Basin in Iran, in the southwestern part of Iran. And over the Karun Basin and even more over the whole of Iran, there was a quite severe drought during and after the rainy season 2017-2018. And already from October on, we could see these very dry conditions that were forecasted for the rainy season. Similarly, only 1 year later, there was a quite big flooding event also in the same region. And this flooding event also was due to very, very high rainfall amounts, especially during March and April 2019. And already from December 2018, we were able to see these kind of wet conditions that were forecasted. So I think this looks quite promising, but at least for us, still a big question is how to really use this kind of information for making concrete decisions and actions. The current forecast that is from now the 1st of March 2021 shows that especially March and May, there might be quite dry conditions. But from June 2021 until August 2021, at least from now on, there seems to become very wet and warm conditions. And this is quite similar to the predictions last year. And I also had a look at the ICPAC outlook for March, April, May, and at least in this small area where we see now these dry patterns, this is quite similar with the outlook from ICPAC, which is of course always a good sign if two forecast products are somehow similar. So last but not least, I would like to show you some links and some ways how you can get access to this kind of information. So the operational forecasts are published on our own KIT data server. And this also includes some links with which you could integrate these kind of forecast information, maybe in external services. So you can access it with OGC services like the web mapping service and so on. So you could easily integrate this kind of information in your own running forecasting system or forecast visualization system. We also have a own decision support system, which was developed by a company in Germany, the GAF AG. And you can go to this website, you can have a look at the most recent forecasts, you can have a look at some reforecasts from the past, you can have a look at the precipitation forecast, temperature forecast, and so on. And we have also published the whole reforecast repository through the WORDS Data Center for Climate. So you can go to this website, you can download the whole set of precipitation and temperature forecasts from 1981 to 2019. And you can also start to use our kind of product. So besides these kind of channels and publications, we already share our forecast with the SMA in Sudan. And I hope that more interested authorities and potential end users might appear after this kind of presentation. So I would like to conclude my presentation with a short wrap-up. So during the last couple of years, we have computed or developed a kind of baseline ensemble forecasting product for the main, which includes the Blue Nile and Tekese-Barra rivers. This ensemble forecasting product contains forecasts or ensemble forecasts for precipitation, temperature, and radiation. It is an ensemble forecasting product, so we have from now on 51 ensemble members at a spatial resolution of 0.1 degree. So the forecast, they have a daily resolution from which we then compute monthly data, and we also compute, of course, tertile, quintile, extreme category forecasts, ensemble statistics, and so on. We could achieve a quite substantial improved performance compared to the raw CS5 forecast, which somehow shows us that we are on the right track with this kind of approach. Furthermore, we have now achieved that our forecasts are released only about 1 day after the official ECMWF release. So CS5 is released on the 5th of each month, and on the 6th of each month, our forecasts are ready, computed and available online. So I also would like to give a very small outlook. So we have quite big plans in the future. We would like to extend the system. We would like to include which is quite obvious. We would like to include drought indicators. We would like to include more variables. We would also like to cover a larger domain, maybe even the Greater Horn of Africa. We would also like to look into new methods for regionalization. So in this case, we would like to look into machine learning approaches. And of course, we would like to link our atmospheric or hydrometeorological forecast to hydrological, crop, and impact modeling approaches. So with this, I would like to close my presentation, and I would be happy to answer questions. Thank you.
Thank you very much for this excellent presentation, Dr. Christoph. And thank you for sharing with us your experience in this regional forecasting and how you reduce the bias and how you use these 51 high resolution models. And thank you also for sharing some useful links also. Thank you very much.
Welcome.
Now, we would like Dr. Kevin from Oxford University. Please kindly introduce yourself and give us like a quick reflection, maybe just in 3 to maximum 4 minutes, Dr. Kevin.
Okay, excellent. Well, thank you very much for this opportunity. I hope everybody can hear me now. This was very informative for me, and it's always wonderful to see everything that's being done. I've been working on the Nile for about 10 years or so, and the notion of data access, data collection is always a challenge. And I think it's a good reminder here that the technology is moving forward very strongly, and the goal of an organization like NBI isn't just reports and studies, but it's to provide regularly updated data products that people can use and to identify the best data products that people can use for historical data, for forecasting data. So that notion of data collection, data QA/QC, quality assurance, quality control, data dissemination are the first things. And the next things are really data processing and analysis. We can see with the move towards remote sense data that a lot of data is available, but the most important thing is transparency to make, especially as things become more challenging, transparency on what is the data that's used as inputs into the model, the raw data. What are the methods and the models that are used to verify and validate these tools? And then what are the outputs ultimately of some of these tools? So I see this as a very interesting turning point for NBI and for the Nile Basin to not take on a role just of doing studies, but really providing information and knowledge. And obviously there's been a lot of attempts at doing this in the past. And I think the move towards the integrated knowledge portal is a great example of hopefully where the basin will go. In my 10 years, there's been a lot of attempts to generate data and knowledge and to disseminate that. I think the big questions here are these methods need to be peer reviewed. They have to be accessible. They have to be open to be trusted. If it's not open, it's not trusted. That's what I've learned since I've been back in the academic world. Things have to be available if anybody's going to trust them, especially if you have international borders and political disputes. They have to be transparent or they will not be trusted. So the question is, what is the role of NBI in this? Currently, as we know, there's products coming out, but what is the real role of NBI as these different groups move forward to provide information, to provide knowledge so the basin countries can plan, not just in a hypothetical sense, but in a very real day-to-day sense. How is that information available? Who has access to that data? How is it monitored? How is it controlled? And how will it continue into the future? So that's all I have to say. But I think it was an excellent session with a lot of wonderful information on where the basin has gone during my time working on the Nile.
Thank you. Thank you very much, Dr. Kevin, for this excellent reflection on this session. Thank you very much. I just would like to ask our panelists some few questions. I know that now we are almost beyond the time. There was one question to our expert, Azab from Intro. To what extent the flood forecasting system produced information that helped Sudan and South Sudan in the exceptional season of 2020? I think you already answered that, Azab, during your presentation, but if you would like to add something, you are welcome, please. Azab, would you like to add something? Okay. Maybe I will go to the next question to Dr. Kim from the WMO. There is one question about high costs. I saw that in the chat. You answered that question. There is another question about, do you have like a group for hydrogeology at the WMO?
Yes, I already replied to that question. Unfortunately, we do not have a specific group for hydrogeology at this moment, but I explained that under the Standing Committee Hydrology, we do have a specific activities related to satellite products to providing some information related to the hydrological perspective. So there is some activities ongoing, and we do also have some linkage with other community, especially it's very much specific topics for the satellite community that they want to engage hydrologists as a user and listen to hear from us what is our requirements and needs. So we have a certain activities, but unfortunately we do not have a special group for that. And I have a question, may I? Because I received some requests from the UN colleagues that they asked about, you know, as you just mentioned, Sudan and South Sudan 2020 flood. And I was not aware about you already have the flood forecasting system in those regions. And can I ask the reasons that why or how it happened, especially that the disaster had a lot of effect and damages, and how is the forecasting system operated at that time, and what was the missing or gaps? And somebody can explain the 2020 flood situation with the operational hydrological forecasting system? That would be very helpful. Thank you.
Thank you. Thank you very much. I think, Azeb, you indicated that you are communicating your forecast to the countries. Would you like to add some further response to our expert from Dr. Kim from WMO, and also the one who asked also about the same thing, Azeb? Would you like to respond?
It appears as though Azeb's microphone is not working right now. In the chat, she's mentioned that.
Okay, I'm trying to unmute you, Azeb. You are muted. Okay, thank you. Yes, Azeb, would you like to respond? Hello, Azeb. Okay, maybe we will come back to Azeb. It seems she has like some challenges in her mic or... Yes, no problem.
Yeah, she just stated that her mic doesn't work and she will write in the chat.
Okay, she will write. She's writing, she's responding in writing. Thank you. Okay, there was one question also for Dr. Christian. It is about information about the rising of water level in Kenya, and of course it is connected to Lake Victoria. Of course, you gave some examples about some reservoirs in the Blue Nile and in the White Nile, like Osiris. But would you like to add any further thing to this question?
Yes, I would like to add something. As I already showed in the answer, that we have this time series for the Lake Victoria available on our database. So if somebody else has interest in different water bodies which are not available on our website, feel free to contact us, and then we can see if this is possible to estimate water level time series from satellite altimetry. At the moment, there are only selected targets available and not all water level time series which are possible to estimate. So feel free to contact me if you need more information.
Thank you. Thank you very much. And to you, Dr. Hussein, there was one question about were these models validated with the real information, and also from other maybe some kind of projected models, but also, maybe it is more of validation of the models. You can respond to that. Were these models validated well? Thank you.
Yeah, thank you, Dr. Mudatir. Yeah, I have already responded to his questions.
Okay.
Yeah, so if he's asking about the WRF model, we have done some assessment, particularly on the products that we are producing. So we have the ERA reanalysis driven WRF simulations for the past 1981 up to 2010. So we looked at the skill of the model in reproducing the rainfall characteristics, particularly the onset, the dry spells, and wet spells. So we have done, and it is really a good one. About the GCMs, because those GCMs are WMO designated global prediction systems. So like the ECMWF, UK Met Office, like the Meteo France, those are the models that we used, and also some the NMME models from the North American multimodal ensemble simulation. So we assess the skill of the models in representing the past climate. What we didn't do is we didn't do model selection. For now, we are just using all the available models. But we know the skill of the models varies from region to region and also from season to season. And in fact, even some models are skillful than the others. So we have also a paper which has been submitted on that. But up to now, we are just using all the available models, and we didn't do any model selection, or we didn't give any weighting for the skillful models. So we just give them equal weight. Thank you.
Thank you. Thank you very much, Dr. Hussein. Now we are reaching the last part of this session. I would like to ask, please, Ammar Jabir, our rapporteur, and also he's kindly also give us the takeaway message after each session. Please kindly, our rapporteur, Ammar Jabir, the Secretary General of International Forum of Meteorological Society, please kindly introduce yourself and just maybe briefly within 3 minutes, you can also give us the takeaway messages from this session, please.
Thank you very much, Dr. Mudathir. And also thank you very much for the panelists. They provide a very excellent work. My name is Ammar Jaber. I am the Secretary General of the International Forum of Meteorological Societies. I have the pleasure to summarize this is excellent work. And as usual, MBI provide a wide horizon of very useful product for the water resource management in the Nile Basin, such as the river forecast system and flood forecast and early warning. And also this data is available for the decision-making support system on the web in the website. Also, there's a forums and there's capacity building available for the countries. And in terms of weather forecast or rainfall prediction, some of the panelists provide the possibility of generating weather forecast for the region with high accuracy, and they applied numerical method, and also they use satellite data, and also they use different technique like downscaling and bias correction. And all this data is available through the website or other means. Some of this forecasting system undergone some improvement through the time, and also through the correction methods. And I think the only problem that they mention is the dissemination of this huge data, and also the application, the availability of the satellite data. It requires better management, and this is we can link it with the big data management. And we have a nice introduction about the big data and how to utilize it in the water resource management, with some challenges, scalability and the dissemination, and how to get some insight from it. We showed some examples from the Rosaris Dam, how we can apply the big data method or data mining. Also, as usual, ICBAC provide very nice product to support the water resource management in terms of seasonal forecast, and also weekly forecast, and the new, I think the new tropical cyclone forecast, and this is useful for the disaster management. And there are some attempts to use the satellite data in Riverflow, and we showed some example, and there is a possibility to employ the satellite data in prediction of the rainfall. I think this is a lot of information. I just tried to pick some key point of them, and as usual, I will provide a very concrete, very comprehensive report about these sessions. And yeah, that's all. Thank you very much.
Thank you very much, our rapporteur, Ammar Jaber. Thank you very much. Allow me, please, to thank all the panelists. I would like to thank you, Ammar Jaber. I would like to thank you, Azab Mersha, Dr. Christian, Dr. Kim from the WMO, Dr. Christoph. I would like to thank you also, Dr. Hubert, also Dr. Hussein. I would like to thank you also, Dr. Kevin, and Dr. Maha and Dr. Muhammad Mustafa. I would like to thank also our team here, Dr. Azza, Patrick, Jonathan, Sued Wamala, and the MBI team who supported many things behind the scene. Thank you very much for this excellent presentation and for this nice discussion. Let us continue, cooperate together and work together. And as I indicated also before, this climate change, it doesn't know the boundaries. And let us adapt well and help each other with sharing information, sharing knowledge. Thank you very much for showing these excellent opportunities. Thank you very much.
Thank you.